Okay, hey everybody, how's everybody doing? So, quick disclaimer. So, for the rest of the week, of the remainder of the week, we will be in here. So, we will not return to the basement, right? Like we say here, it's a bit cozier, but I see like that some of your colleagues already decided to not show up anymore. So, like maybe we have a little bit more air this time around. Okay, cool. So, let's dive right in. Today, we actually have a larger block about disentanglement, right? So, this will be like not the 30-minute block, but more like closer to 60, maybe even 90 minutes, but we'll still interrupt it for the 5 and 5s. Okay, so when we talk about disentanglement, right, we usually talk about latent spaces. So I don't have a motivating slide for this, so I'm going to do this just by words. So what does disentanglement mean? Disentanglement is the idea that if you actually have like some latent representation of your knowledge, like as we have in generative models, right, then the idea is that we can introduce some kind of structure into that latent space, right, that allows us to have a more interpretable like latent space, right? So like, and this process of basically going from this very unstructured to structured latent space is called disentanglement. And again, so we usually refer to this in the terms of, or like in the context of generative models. So if you've seen, again, like for me, show of hands, how many have been in the advanced AI or AI2 lecture? Okay, so for you, there will be some repetition in terms of generative models, right? But like also like the additional disentanglement view on it will be new, but there will be a little bit of an overlap there, right? So what is a generative model? Like a generative model is a statistical model that is capable of generating new data points from underlying distribution of a given target data set. So for instance, let's assume we have this set of dogs over here, right? And we kind of want to generate a new dog, like a new cute puppy, right? So the only problem is that we actually don't know what the distribution of puppies are, right? So we don't know what the good distribution of dogs is here. So sampling from this unknown distribution becomes problematic, right? Because this is like a not only a structured and complex, but most importantly, an unknown distribution here. Doesn't make sense, right? Like, so if it would be just like Gaussian noise, we could easily sample this, no problems, right? But since we want to sample something unknown, we need to find a way around this, right? So how can we do this? Instead of sampling directly from this complex distribution, what we do is that we learn usually a mapping in some way, right? Like, and there's different approaches how to do this from this from a simpler latent distribution, for instance, Gaussian, right? So we can sample from this Gaussian, we get like some latent vector. So what we usually describe this as is basically P of Z describing the distribution over a latent space, right? And Z then being a latent vector. And then if we actually learned some kind of mapping from this like simplified space to this more complex space, we can then use Z as the seed, so to say, right, or as a starting point to generate this more complex sample, right? So we kind of model this again in a distributional way that we say we have like this conditional distribution that is able to generate X, which is samples from our complex distribution, given Z, our simple distribution, right? So like in this case, we have the distribution or the prior over Z, and then the conditional distribution producing our X's, right, our complex samples. And currently there's 3 different like prevalent generative models. So, and like those would be variational autoencoders. They're also the oldest ones of the ones that we're going to talk about today. There have been GANs or generative adversarial networks, and there have been the fusion models, right, the most recent. And well, there's the saying that a picture is worth more than 1,000 words. So I asked last year already ChatGPT, I believe, or DALL-E, this might have been DALL-E, to like visualize the difference between these models. And this is what we have from left to right: VAEs, GANs, and diffusion models. Okay, so any questions? I'm obviously like not going to leave you with these images as an explanation. I hope that was clear, right? So, but in general, like we can actually do like these kind of other versions. I don't know how we ended up here, right? But yeah, so that tells you a little bit about using a generative model to explain generative models. So let's draw images ourselves, right? So like, or pictograms. So VAEs, in a very, very brief nutshell, are basically exactly the idea that we just discussed. So we have our latent representation Z, and that one basically is used as a conditional in our like generating distribution X that gives us then like the new samples. But in order to get there, we kind of have a reconstruction loss where we start with a data set that we know already, right? We take samples from this data set and we learn how to project that one into our lower dimensional space, Z, and project it back up again to X dash. And we'll talk about this in more detail. GANs, compared to this, slightly go a different route. There, the idea is that we directly try to start from an unbiased latent space, right, from Z, and generate X's. And the idea is that instead of learning a encoder, we learn a discriminator that basically should distinguish between samples that we generated from our generator and samples that have been prevalent, like have been existing in our data set, right? And once this discriminator cannot discriminate anymore, we assume that we're like as close to the original distribution as it gets, right? So again, we will talk about this in more detail. And then finally, we have diffusion models, where here the idea is that we're basically going to add noise to our initial distribution, right? And then like go all the way down until we basically have only like samples generated by noise, right? We just, again, if we have Gaussian noise, this is a distribution that we can sample from, and then learn how to undo this noise editing, right? So instead of like projecting into low dimensional space, we basically have this approach there. And we want to talk about all of these three methods in a bit more detail now, but this would basically be the picture that I would have hoped for when I queried DALL-E for this one, right? So something like this, but this gives like a very brief overview. So now how does this entanglement come into play here? Well, if we now, for instance, look at any of those latent spaces, right? So be it latent space for diffusion or like for VAEs or for the GANs, right? So if we look at it, and it might look like something like this, right? So let's say we have like our 4 data points in our latent space, that right? And then if we produce our X out of it, we have those 4 shapes, for instance, right? So this more complex sample, right? So I mean, sampling in 2D, not a problem, and then getting those like larger, more complex samples, also great with the GAN model. But the question is, what are the actual X's here, right? So we basically, at this stage, if we just learned without any additional knowledge, any additional injection, right, or any additional losses, we kind of can do post-hoc analysis on those, right? So as we've seen before, but questions like, is this like, how can we maybe structure our whole learning problem to begin with to have like something more intuitive or something more interpretable along these axes, right? So this would be like the entangled space, right? So we don't really know what Z and X are, because even if you look at the samples, right? So A seems to be high up, okay? So D also seems to be high up. So maybe it's the square, like being square-ish, right? Could be on the Y-axis and so on, but this is something that we need to interpret, right? Whereas if we have a latent space that looks like this is significantly more interpretable, right? So who wants to give me an idea what this could be?
Like the Y-axis is like color, like X is shape.
Yeah, exactly. So this is like, this immediately basically gives you more room to interpret, right? And this is what we would call then a disentangled latent space, right? So the idea here is that by having something more structured in a latent space, right, or like in particular, this disentanglement means that we assume that there is some like underlying representation that can be projected on independent axes. Like the independent is here the crucial term, right? Independent axes. Yeah. Does this make sense? Right? Okay, great. So again, so what are disentangled latents or disentangled representations? So in this case, we will abbreviate it through DRL. That this, in this case, it's not deep reinforcement learning, but disentangled representation learning, right? So disentangled representations are distinct, independent, and informative generative factors of variations in the data, meaning axes in a latent space, right? So independent meaning that if I move one of them along, like I get still something meaningful along the other. So if I change shape, right, then I can get like squares like in blue, and if I move it over, I get circles in blue, but the color itself is independent of the shape, right? So basically, if we move then the color on the different axes, we only change the color and leave the shape alone. Make sense? Excellent. So again, in this case, this doesn't have to be like on a per axis basis. You can also have like vectorized disentanglement, so like entire let's say several elements of your feature space or of your latent space belong together and together represent something, right, which is disentangled from the rest. But yeah, so the idea here, for instance, would be if we would like try to encode some samples like these into a feature space, that those different like subparts like could be the object size, object color, and also like floor color, viewing angle, and so on, right? And this does not mean here that we inject this knowledge a priori already, so that we say like, oh, this is our latent space, and we want to have this and that and this, right? But instead, we kind of want to encourage, right, the latent space or the learning of the latent space to have like these independent axes, and with the assumption that this independent axes will be more interpretable than correlated axes.
What about if only part of the space is more, or rather is disentangled? So are there approaches where perhaps disentangling the whole space wouldn't be feasible because it's just complex? So you do it with only a fraction of the features?
I don't. So again, like, I mean, you could. So for the recording question is if it's possible to just like disentangle part of the latent space, right? I mean, sure, you could do this, right? Like you could have like, for instance, two different encodings and say like, okay, this is like this latent vector is supposed to be disentangled and this one is supposed to be like just scrambled, and then afterwards you put them back together. But the question is what the benefit of this would really be if you're able to maintain the performance with a completely disentangled latent space, right? If you don't actually sacrifice anything in terms of performance, right? Then the question is what this remaining scrambled latent space would offer you, A. And B, the other question then would be if even if you drop in performance, if you have now the scrambled space and the disentangled space, right? Then the question is how much weight does the decoder stage actually still put on the disentangled space, and how much does it just leverage the entangled one, right? So you would have to put additional like weight in terms of something like this to basically like maintain this dependency, because you actually want to make sure that all of the information gets, or a lot of the information gets put onto the disentangled space, right? And I don't know how successful this will be if you offer this less structured approach still, right? Like of just like scrambling the data, like having this entangled latent space, because that's obviously like easier for the model to put information there, right? Because it doesn't have to find anything, any representation that is entangled and contain the information. Yeah, and you can do like really cool stuff with this, right? So if you actually have a disentangled latent space, interpolation across individual interpretable axes becomes a thing, right? So for instance, like my favorite part here would be the species interpolation. So you have one axis in your latent space. Again, axis doesn't mean here individual elements. It could be like also several elements together, but like you have one axis along your latent space that allows you to interpolate between a dog and a lion, right? And then you have like I don't know what you want to call it, Lyog or Dian. I think Dian sounds nicer. And you have like something, right? Like something in between, which is really, really neat. Or like going from cats to dogs. Yeah. So this is kind of like the beauty of this entanglement here. So again, you have some form of explainability in your DLR, right? Because ideally you can you find meaningful axes, right? Or the hypothesis is that this disentangled latent spaces that are just as performant as the entangled latent spaces are more interpretable because they correlate more to concepts that we also understand, right? Again, here, for instance, one axis would be species, right? And this is a concept that we as humans also understand, right? And there's also this argument for generalizability, meaning that if you have individual axes along which ones you have to like can separate your latent space, and then something in your observation changes, but it like you can like the change that happened there will only affect one of the axes. All the other ones will still be able to provide meaningful information. Whereas if it's scrambled, then a significant change might also affect the entire latent space, right? Because of this like entanglement. Yeah. And again, if, for instance, if you want to produce certain outputs in your generative model, and you just want to say like, oh, like I only want to have, let's say, like a park as potential backgrounds, then you take the axis that correlates to the background and put it on the park value, right? And then you will only generate park backgrounds, right? Does it make sense? So that's actually, there's a lot going for it, right? The question is now, how do we actually achieve it? Mm-hmm.
If you disentangle the entire space, then you have to give, for example, in the vector operation, for each value of vector, you have to define what it means. But no.
That's explicitly, so the question was like interrupted, so I don't know where the question was going, but so far the premise was that for each individual like space in my feature, I need to define what this axis would be. And as I mentioned before, but like maybe highlight this again, the idea is not to structure it like with biases that you actually introduce and say like this element corresponds to this axis, this axis corresponds to this concept, and so on and so on, but rather you encourage your model to have independent axes, right? And then afterwards, you go and check what these axes might correspond to, right? So again, the interpretability, the explainability here is an assumption. It's not a given, right? So you could think about doing something where you explicitly like insert concepts that you want to know and like basically seed your axes, right? Like you can do this kind of thing. But like in general, this is not what we're doing with like most, and none of the methods that we will talk about today does that, right? It's all just about encouraging independence in the latent space. That's what it is, really. Okay. Does this already address the remainder of the question?
Yes.
Excellent. Okay. So we're now going to talk about disentanglement in VAEs, in GANs, and in diffusion. But before that, I think it's valuable to give like a quick introduction to all of these generative models first before we go into how to like introduce disentanglement in there. So again, variational autoencoders, the idea is if we have like this complex space, right? We have some observations, some samples from this complex space that we don't know about, or that we don't know how it's exactly structured. We would like to learn estimates, right? Or like to learn the underlying distribution, and we're going to estimate this through like some like variational approach, right? So once we know what the distribution actually looks like, or once we're able to know this step, we can generate new. My animations are completely messed up. I'm sorry for that. So once we're actually able to learn this, I can see my cursor. Okay. So once we actually learn this kind of model, right, we would be able to generate our complex samples. That's the overall goal, right? So we kind of want to have a parameterized model. That's that.
Yeah.
Okay. Good. Okay. So how can we do this? We start by like assuming that we're going to maximize our MLE, so maximum likelihood approaches here. I'm just assuming that you'll have that much machine learning background that you know what this means, right? But usually what we kind of want to have is that we want to approximate or compute the log of our marginal distribution, right? So the first step that we need to do though, because we cannot do this directly, we kind of want to approximate this or like use like an additional, we want to introduce this lower dimensional distribution, right? So now how can we introduce something without actually destroying the equivalency? Well, we could multiply it by 1. And one way of writing 1, right, would be basically the integral over our conditional distribution, right, over the actual random variable, not the conditional variable itself, right? So I think everybody should know from basic statistics that this integral like evaluates to 1, right? So we can just multiply it without destroying any equivalency. And then because this one or this part here is just a factor, right? Now for this integral, we can pull it inside the integral. This is exactly what gets us here, right? And then in addition, what we can also do again is multiply one more time by 1 inside of this log term here, right? Where we basically introduce again the same conditional auxiliary distribution as we did before. So why would we do this? Because this basically goes already towards something that looks very much like a KL divergence, right? So we actually are able to use afterwards measures that we know from machine learning very easily to approximate our original marginal distribution. So now what this allows us to do is that instead of drawing samples from the marginal directly, we can now draw samples from the conditional distribution from this fellow over here, right? Or actually, sorry, from this fellow over here. The only thing that we did here was basically Bayes' theory. In order to get from this step to this step, this would only be Bayes' theorem. Do you see? Wait, you're familiar with Bayes' theorem, I assume, right? So do you see how we get from this step to this step? Right? Excellent. So again, this is completely equivalent. There is no approximation here so far, right? Which is really beautiful because now we don't need to draw from our marginal anymore. It suffices for us to draw from this conditional distribution, which can become significantly simpler if we actually get Z, right? Of course, what we need in addition is this prior distribution, P of Z, and we need this posterior P of Z given X now, right? But this is like an issue for the next steps. But for now, this basically allows us to get rid of P of X altogether, right? Okay. So and then from here to here, the only thing that we do is basically we scramble around like some of the terms, right? So we literally just moved P of X given Z before the fraction and then switched those two fractional terms, right? That's all that happened to get us here. So why would we do this now? Because we have now a log of products, and this log of products we can write the same as the sum of logs, right? So this is also again something like should be very familiar. And then if we have like an integral over sums, we can have the sum over the integrals, and that leads us to this upper line here. So why do we do all of this now? Because if we actually look at these equations, we have two KL divergences, right? Which we know how to compute. And we have one reconstruction loss, or like rather expectation in this case, right? So where we say like, okay, Z is drawn from this conditional distribution here, right? And then log of P of X given Z. And one further step that we can see is that given that the KL divergence will always be larger than 0, right? And we're trying to approximate this one, we can just get rid of this fella here, and we have like a lower bound on our marginal, right? So because this one will always add to the bound, so getting rid of it gives us the lower bound, right? And this lower bound is usually what we refer to as the elbow, or the so-called evidence lower bound. So there's still like one open, and by doing this, basically we get rid of the posterior distribution altogether, right? And we're only left with those three terms. So the only thing that we have an issue still with, right? So those two are learned, right? So that's why we give them the learned parameters, but this one is given. And this one is what we call our prior distribution, or a true prior over that. And what we usually do is that we assume it to be like an isotropic Gaussian, right? So a zero mean standard variance. And that's what basically gives us the final elbow, right? So does this derivation make sense? Was there any step in the derivation that you didn't fully grasp?
I think I understood the derivation, but I did not get why we calculate log from P.
Okay. So in order to approximate basically this distribution, right? We do this through like the maximum likelihood estimate, right? And in the maximum likelihood estimate, we basically have this log P theta of X that we need to compute, but we don't know how to compute this. So we need to somehow approximate this, and we do this like in a variational way. Basically, variational in this case means introducing auxiliary distributions to approximate that one, right? So like this is the thing that we're trying to optimize, right? But we don't know how to compute it. So instead, we approximate it, right? And we do this basically through this evidence lower bound. Does it make sense now?
Yeah.
Okay. Yeah, again, so now our new goal now becomes basically to optimize this evidence lower bound, right? In our expectation, like which would be equivalent to maximizing the likelihood of the observed data. So again, if we have like this very high dimensional data that we don't know, or high dimensional, or like highly structured or whatever that we don't know how to sample from, right? We can then train our encoder stage. And in this case, we basically would produce the mean and like the standard deviation, or if we want to learn the actual full covariance matrix, usually what you do is you learn like the lower triangle of the distribution of the covariance matrix, right? So that gives you these pieces, but in the variational autoencoder part, in contrast to the normal autoencoder part, we then use those in a distribution to actually generate or to draw then from a latent vector, right? So in a normal autoencoder, without the variational part, you would directly compute the latent vector from the encoder. In the variational part, you actually encode the parameterization, and from that you draw the latent vector, right? Does it make sense? And the equations here basically would tell you how to, for instance, to draw this one. And then with the decoder stage, we then project back from Z into this high dimensional or like this highly structured space, right? And all of this happens basically simply by optimizing for the evidence lower bound, right? Are you allergic to dogs by any chance?
No, I think from anything else.
Okay, good. Because if you are, right? Okay, cool.
For 5 minutes and then it's gone.
Okay, excellent. Yeah, so just quick pointing out here, this operator denotes the Hadamard or the element-wise product, just for your information. Okay, cool. So any questions about this so far? No? Okay. And with this, we basically get here like this whole stage to get from X to ZI. So basically meaning encoding or going through the encoder, like getting our parameters, sampling our latent vector. That all corresponds basically to this to the conditional distribution Z given X, and analogously, like producing X given Z would correspond all the way from like inputting the latent vector through the decoder and getting our X directly. All right, so those basically would be corresponding to these terms. Oh, you cannot see the person, to these terms here, right? These steps. Okay. So now during runtime, what do we do? Like if we actually still want to create, or if we want to create like images of dogs and so on, right? As you know, we cannot directly do this, but what we can do is we can sample just like Gaussian noise, right? So we get basically our P of Z here, and then we use only the decoder to generate these images. And that's what makes this whole thing a generative model, right? So with this, hopefully, like you understand now what VAEs are, or how they're trained, how they work, and where the elbow comes from, right? And this basically, again, the upper picture here is an approximate, like it's a detailed depiction of the intuitive sampling here. Okay. So now how do we introduce VAE here? So we first, how do we introduce entanglement? Again, this is the same loss as we've just seen, right? And the true distribution is usually intractable, right? Or not really known. So we like, again, just repetition, use basically elbow loss to approximate this, right? But now the true posterior distribution is also like, or the prior distribution here is not known. And we assume a zero mean isotropic uncorrelated Gaussian. So what does this actually tell you? So what does it mean that we have this isotropic prior for the latent space?
Maybe that the axis in our latent space are uncorrelated.
Uncorrelated, i.e. independent, right? So the prior already gives us the disentanglement, right? So the prior already kind of like encourages disentanglement. What's the problem? Why is our latent space not disentangled yet? Oh, well, I mean, the prior is an isotropic Gaussian, and we encourage latent representations, obviously because of the KL, right? Because we're trying to push our conditional distribution closer to the isotropic Gaussian, right? So the KL term is actually what tries to push our learned distribution towards this independent space. So why is it not independent yet?
Are we optimizing the lower bound and then?
The KL is part of the lower bound. Right, this entire thing is the evidence lower bound. There were two KL terms, right? Yeah. So, but maybe like to add on to this, the KL is just one part of our loss, right? There is also the reconstruction loss that basically counters that one. And if you think about it kind of in a Bayesian way, then your prior usually provides initial guesses, but with more and more data, with more and more evidence, you are allowed to deviate from the prior, right? And you will deviate more and more from the prior, right? Does it make sense? So what we can simply do in order to encourage like disentanglement stronger is we just, and this is as plain as it gets, right? We just add an additional weighting term on the KL term of our elbow, right? We literally just use this like weighting term beta, which gives rise to beta VAE, which means that like the larger we do make this, the more emphasis is on maintaining this disentangled latent space, right? Of course, this penalizes now the reconstruction loss, right? Make sense? But it's really as simple as that. So, but like, why does this actually like work, or like some additional maybe information theoretical perspective on this, right? So, but before that, like a quick recap, just in case you've never heard of it, like entropy is a measure of uncertainty on predictability of a random variable, right? So then we have like the conditional entropy, which would be the same thing, but given another random variable, right? So the uncertainty given another random variable, and then the mutual information measures basically the amount that X and Y would share, and it can be written as a difference between the pure entropy and or the marginal entropy and the conditional entropy, right? So, and it's symmetrical. So mutual information is basically something that tells us, okay, if I have two different variables, they contain the same information, right? Or like there is this shared information between them, right? That's important, the shared information there. So why is the shared information relevant for us in this case? Well, if we actually try to break everything down and we kind of want to see like, okay, our mutual information is supposed to, or our encoder is supposed to still produce good, like high fidelity or like important correct samples, right, from our generative model. But we want to have a structured latent space. The structured latent space might contain information that is or we ideally want to push it towards something where the only relevant information is the one that is necessary to generate our complex sample, right? So we kind of like to want to ensure that all of this information is present. So we kind of want to maximize the mutual information between our latent space and our produced space, right? Or actually what we want to be precisely here is we want to say like we want as much mutual information in our latent representation and our output, right? So the generated samples, while minimizing the mutual information between the input and the latent space, right? So we basically want to remove all the information that isn't necessary to produce our good output. Does it make sense? So, and this would be the weighted mutual information term here. And if we actually look at our elbow of our weighted elbow, then we can see that this looks very similar, right? In fact, and there is like this, or the reason why it looks so similar is that the KL term is actually an upper bound to the information, right? That can be transmitted through the latent channels per data sample. So, and this is why this evidence lower bound actually like approximates the difference in mutual information. And this gives us the so-called information bottleneck perspective on this whole thing, right? So this leaves us then finally in the beta VAE with this modified example, or modified objective here, where we introduce like an additional weighting term on the KL divergence to the prior knowledge, right? To the prior. And we do this in a scheduled way. So basically we don't want to jump right in, because if we do this right away, it becomes significantly harder to train, right? So what we do instead is that gradually over time or over the iterations, we will like increase our Z value, right? And hence like in the beginning, basically be more structured, and towards the end, try to be like to make this like entanglement less and less important, right? Or this disentanglement less and less important. But in the beginning, we kind of want to say like, okay, we start completely disentangled and then kind of calm down from there. Okay, so that's it about beta VAE. Any questions about beta VAE before we go to the second idea? So how do we, like, again, maybe in a nutshell, beta VAE, how does beta VAE encourage disentanglement?
It wastes the term that encourages disentanglement more than the normal VAE.
Why do we have a term already that encourages disentanglement to begin with?
Informational.
Yeah, because the information bottleneck that is encoded, but like mostly actually rather even that we have this prior assumption that our latent space is disentangled, right? Our latent space is an isotropic Gaussian, which by definition is disentangled, right? And we have this prior assumption in VAEs, and the only thing that beta VAE does is basically make this prior assumption stronger, right? Okay, so
Can I ask a question?
sure.
Can you go to loss function to us?
Which one?
On right side. I don't know. Distribution. Yes, here. Why you subtract the chiral divergence from the loss function, not make loose loss?
Because we're basically why would we do? Because we kind of want to I mean, you haven't been here, but like we derived the entire.
Yeah, you guys have.
We derived the entire loss, right? And the cal like is subtracted here in this derivation. Maybe like in self-study go through the derivations, right? But okay. So the second approach for VAEs that I want to very briefly talk about would be the factor VAE, right? Similar idea, but in like now, in addition to our like elbow, we introduce this term here, right? And this is what we usually call like the total the total correlation in this case, right? And Q dash basically is a distribution that assumes complete independence of the elements of Z. Does it make sense? Right? So the total correlation measures how correlated the elements in the or how dependent the random variables are, right? And the idea is, or the dependence within the random variables, but the idea is that this tells us kind of if we have a correlated latent vector or not, right? Because like in a correlated or in a disentangled vector, there would be practically no correlation, right? There would be each element would be by itself. So we do this by now punishing the total correlation. So adding it to the loss and saying like, okay, we want to have as little total correlation as possible, right? So how do we like, where do we actually get now these independent samples from? What would be the idea? You're aware that like if you have a latent vector or like if you have a like multivariate random variable, you can look at it as like basically a set of correlated or uncorrelated scalar random variables, right? So here the idea is that basically we say our vector is completely like there is no, if you look at the covariance matrix, the correlation is all zero, right? So that's what this assumes. Okay, so how would we get this? Well, one way would be, okay, we marginalize it out, right? We compute all of these marginals, and then we just have the product of the marginals, right? But that becomes like very infeasible in practice, right? Because we have this giant batches, they have like super high dimensional latent spaces and so on. So it will become problematic for you, right? So that's not what we cannot do. So what we can do instead, though, is that we can approximate these marginals by scrambling our data set, right? By randomly shuffling through our batches, right? So per dimension, so per feature. You remember how we did this in the past, like in feature importance and these kind of things, where we like created those Frankenstein samples, like something very similar here. And the idea is by doing so, we don't actually get the really uncorrelated vectors, right? But we get like an approximation thereof, right? Okay. And now the thing is, if I now actually have my actual encoded sample like Z and this approximation, or let's just call it like the uncorrelated or the permutated sample, right? If those two are the same, or I cannot distinguish between them anymore, right? Then that means that Z is uncorrelated. Does it make sense? So that again basically tells us how we can solve this KL here, or how we can approximate this KL instead of computing it directly, right? So we can just use an additional classifier with cross entropy loss. And this is what we're doing here, right? So we basically have our normal VAE. We then scramble our latent vectors, right? The Z, and then train or have like an additional cross entropy loss that measures like, okay, how much do they, or how much can I actually distinguish between those two? And if I cannot distinguish between those two, then my samples, or like the actual Z samples, the actual generated ones, are uncorrelated. Does it make sense? And this is like the second version of how to enforce disentanglement in the latent space of a VAE, right? Okay, I think with this, we're already at 40 minutes. So we should definitely do like a 5 and 5 now. Okay, so let's do 5 and 5. Oh, any questions before we do that? No? Okay, let's do the first one. They should stay close to uncorrelated. Does it make sense?
Yeah, okay, kind of.
The way you're laughing. Does it not make sense?
No, it's okay.
Okay.
I have to look into it for myself.
Okay, but like you understand that basically, like if this term wouldn't exist, right, and we would add a beta here, this would be beta VAE, right? But instead we basically say like no, like we leave this prior assumption for the encoder as it is, but we say like that the Zs that are produced, right, should be uncorrelated. Okay, cool. Okay, so this is increment in GANs. So let's look at GANs a little bit, right? So in GANs, like if you look again at our, sorry, this should have been animated. I don't know why it's not, right? But so the idea is that originally, if we look at VAEs, right, we always have like this idea that we kind of train it in a way that our input distribution or like the decoder basically matches whatever we have in our input distribution. But that's not really what we actually want, right? So what we want is that we produce X's that, or differently, we don't necessarily want that the output of our decoder is part of our data set, right? It should just look like it's part of the data set. There's like a bit of a distinction. Does it make sense? Right? So this reconstruction loss that we have might not be the ideal loss to have here, right? So what can we do instead? So what GANs say instead is that, again, the animation here is slightly off, is that assume I'm just starting from something unbiased, right? Like just like some generator and have like random, like Gaussian noise initial latent representations, right? And then what I want is something like a generator that can fool me, right? So the generator should produce samples. And if I look at some random sample from my X data set and some random sample from the generator, I should not be able to distinguish between them. That is what it means that our generated sample looks like it's from the data set, right? So like you sometimes give me like two X's, right? Or like you give me those in random order and I'm supposed to tell you which one is from data set and which one isn't. And if I get like a 50-50 chance, right? So if I'm 50 times of the, like 50% of the time, 50% of the times I'm correct, that basically means I'm random, right? That means that it's as good as it gets, right? So now the idea is that instead of having me like telling you which sample is fake and which one is real, we just basically produce or like train a separate model, like the so-called discriminator for this, right? So now we have like a parameterization for the generator, but instead of an encoder, where the generator kind of corresponds to the decoder part, but instead of an encoder, we have the discriminator. Does it make sense? And that's really all there is to the GAN, or like or to the idea behind GANs, right? But we do record again, right? Okay. So how do we train it? We just treat it as a normal classifier problem. So if you look at our binary cross entropy loss, right? We will not derive this loss in the lecture, but it's like fairly straightforward and like nice for self-practice, right? We basically have like the probability that it is part of the sample and the probability that it is not part of the sample, right? So if the sample is positive, yi, so meaning that this one is part of the data set, or depending how you structure it, or part of the generator, right? Let's say if we want to say it's part of the data set, then y is 1, right? Then we encourage a higher probability for our classifier. So meaning that's where the minus log p theta x comes from, p phi x comes from, right? And if it's like if it's negative, right? So it's not part of our data set, then we kind of want to have a low probability of our classifier. So we want our classifier with less probability to say that is correct, right? That is part of the data set. So in our case now, right, the probability is given by the discriminator, right? So instead of p phi of x, we have our d phi of x, and our negative examples, right, are always given by the generator, right? Makes sense. That those are basically our fake examples. And this leaves us with the actual GAN loss. We can rewrite it slightly, but this is what we usually do, right? So this is our GAN loss, what we optimize. Any questions for how we get to this loss? Should be straightforward, right? So I don't want to, because we were already way over time, kind of want to speed up a little bit. Cool. So again, right, or again, that's images. I don't know why I repeat it so often, but this is like, this basically started, I think, our latest kind of craze of over deep generative models, right? The problem with this one is that they are notoriously hard to train. So there's a lot of like issues with this, right? So for instance, instability. So you can actually end up, if you learn too quickly to generate good models or like good samples, right? Like that your discriminator never gets enough learning signal in order to do anything useful. And the other way around, if your discriminator learns too quickly, then your generator will never get the chance to produce more realistic images, right? So they're very hard to tune. They're very hard to train. So that's kind of what made them very quickly go out of fashion, right? Nevertheless, they actually can produce pretty cool images, right? So this is from this person does not exist.com, right? And it's quite nice, quite nice work. And with this knowledge, we now know where this picture comes from, right? So again, this is just like a very brief illustration of how the GAN, for instance, would relate to the VAE, as we've seen in the beginning. Okay. So we have now our GAN in a nutshell, right? So this is again everything that I just talked about. And the question is now, how can we introduce disentanglement in this construct, right? Yeah. Any idea real quick? It's not as straightforward as VAEs, right? So how many of you actually know about GANs or have known about GANs before? Okay, not that many. Okay. So the idea how we actually introduce the disentanglement here is actually by introducing an additional kind of like conditional term here, Z, right? And we basically say like, okay, if we actually are able to produce this Z, right? And Z is, let's say, simpler, right? Or like it's one hot encoded or something like this, right? Where each Z would correspond to a different concept in our entanglement latent space, right? So like Z1 would correspond to shape, Z2 would correspond to something else, or like the element of C would basically do this, right? And we can kind of like encode this through mutual information and say like that this information in Z corresponds or is sufficient to produce our actual images, then Z would be our disentangled latent space. Does that make sense? Not Z, so C. This seems to be not clear to people. So basically, how can we write this? Or how can we make this clear? So we kind of we kind of make this seem clear. So in this GAN operator, right, we kind of introduce this additional term into our latent space, or we create a second kind of latent space, right, which would be like this classifier vector, right? C. And if we actually end up with like a latent space that looks very similar to Z, something like this, you agree with me this would be disentangled, right? So we enforce this by training the classifier, or be like training basically a generator where we're able to directly abstract which class was basically underlying this generation, right?
Get a little more capacity.
Potentially, yes. So the question was if this would limit model capacity. Yeah. And because we also have the shared like convolution layers between the classifier and discriminator, that enforces basically this dependency on C even more.
But we still have an entangled part of the latent space.
Sorry, what part?
We still have an entangled part of the latent space, right?
Yeah, so the idea, again, is by basically enforcing the similarity, right, this entangled part will become more disentangled. I don't have any more slides for this. So maybe take a note for next year, more slides on InfoGAN. And I thought this was like, I mean, basically what we see here, like, okay, let me try to explain this like yet in a different way. Like, you have understood the connection between mutual information and disentanglement, right? Like we did discuss this in the VEE part. And here we compute the mutual information between Z and the generator Z and Z and Z together, right? Which basically means that there should be a lot of information in Z as well as in the generated sample X, which basically means that if Z is disentangled, which we enforce because it's just like a label, right? Or like the multiple class labels, right? Then the G of Z given G of Z given Z, this is like a tongue breaker, basically also only or like relies on this shared information only, right? Because again, mutual information is symmetrical. You're laughing because you think like I'm not helping, right? Okay, think a little bit about it. Yeah, and then maybe we'll talk about this in more detail like tomorrow again. Maybe I'll pick it up again and try to explain this even in more depth. But yeah, that's basically what InfoGAN usually does. Yeah. Like I think that's the common the usual loss that we're using for the GAN. Yeah, you're right. Like the equations are not really that well matched here. Okay. Like make a note, rework the whole InfoGAN.
During inference, we sample from Z.
Yeah. Yeah. During inference, we only sample from Z. Yeah. Unless we kind of want to, like, you could theoretically still sample from Z and basically make one class more prevalent or less and so on. Right? Yeah. But let's move on to something that I have more slides about, right? Disentanglement in diffusion. So, I mean, the reason why I didn't put so many slides for GANs is because again, GANs are kind of out of fashion and like the new kid on the block and current generative process is diffusion. So how many of you have heard about diffusion? Okay, how many of you know how diffusion works? Less. Okay. How many of you know DDPM-based diffusion and score-based diffusion? No difference between those. Yeah, wonderful. Okay, so in a nutshell, like diffusion basically is the process of destroying like something with a lot of information, like a state, like or moving from a state of a lot of information to a state of quasi-noise, right? Like or barely any information, right? Through iteratively adding noise or iteratively destroying information. So and the idea is that if we can actually describe now how we get from like this like information rich state, right? Like the image of the dog, right? To a completely like noise state or quasi random state, right? Then maybe we can also learn how to undo that process, right? So diffusion is actually the step of doing this, and the denoise, or like the reverse step, is what we call denoising, right? Sometimes also the reverse step is called diffusion or reverse diffusion, but the reason why you can actually call it the same has to do with math, because basically both can be described as an SDE, so it doesn't actually matter in which direction you go with your stochastic differential equation, but we're going to talk about that in a second. So yeah, and the idea is if I can actually learn it, right? So if I know actually how to get from structure to noise and noise to structure, I can now generate samples from only my noise, which I know how to generate samples, and produce from that, or generate from that, and afterwards samples of the unstructured information, of the structured information that I don't know how to generate. And that's basically like what we've seen all the time so far, right? So we have the forward diffusion, or like this is a typo, it should be just either reverse diffusion or just denoising, not reverse denoising. That makes no sense. Sorry for that. Did we have that last year already?
No, we had it in the AI and I fixed it.
Why didn't you fix it here? Okay, so now the question, doesn't that just look like VAEs? So for those of you maybe that like that are familiar with VAEs, or like now all of you are familiar with VAEs, who thinks that this just looks like VAEs? None? At least one person, two person, okay. Or was this like, or did you want to say something?
I could explain why it looks like VAEs.
Okay. Okay, But okay, so let's revisit VAEs really quick, right? So we basically have this whole process that we have the encoder stage and we have the decoder stage. And then during inference, we basically just introduce noise or like a Gaussian sample, right? And generate basically our complex sample, right? So in forward diffusion, or like in diffusion, the forward process, what this means is like we kind of have this step, right? So something with the colors is unfortunately off. So this should still be green, but whatever, right? Like just go with me here. Right, so this will be the diffusion step, and then we have like our denoising step, right? So we go again from noise to this thing. So the question to all of you, are diffusion walls just VAEs? So who thinks yes? Okay, you think yes? Okay, so they're not. Why? What is different to like normal VAEs? And some of you have seen the lecture already, so you know. Say it.
The latent space is in diffusion, it's not reduced to lower dimensions.
That's not what I wanted to hear.
Okay, the encoder is not learned in diffusion.
That's also not what I wanted to hear. What's the first thing?
Not remember.
So first of all, we talked about like iteratively adding noise, right? So diffusion is an iterative process, right? So it's not like a instant like not a one-step process is in VAEs. So now we can say, okay, we basically go iteratively and produce more noise, right? And then decode that part, right? So the question now becomes, is like diffusion just a hierarchical VAE? And now you took all the fun away, right? So let's continue. So why is it not just a hierarchical VAE?
The latent space is not reduced.
That is correct. Excellent answer. So in the diffusion, usually we don't have like this, like a low dimensional latent space or like this low dimensional noise projection, but we just add noise to the image in the first, or like to the data in the first place, right? So we basically add noise, right? And then we decode. So the question is a diffusion model just a hierarchical VAE with high dimensional latent spaces? Go ahead.
The encoder is not learned.
Exactly. So the encoder is not learned in this case, right? Because the encoder is just adding Gaussian noise to it, right? So the question now becomes, is diffusion like simply a hierarchical VAE with high dimensional latent spaces and analytical encoders, right? So who thinks that this is the case? Okay, yeah, obviously everyone, because the page is full, right? And there's no space anymore left. But like, yeah, so at least if you consider the DDPM-based approach, because this is what DDPM represents, right? Like this hierarchical VAE perspective, right? And I don't actually think that matters at all. Okay, so again, what does this mean? If we have like our very structured, complex latent space that we don't know about, and we have like different, like for instance, dog images. So this could be like a latent space that I at least don't know what the distribution of a dogs looks like, right? Or dog images rather. But we have this, and we don't know how to sample from that. Again, by basically adding more and more noise, you can see that those images become to look more and more alike, right? So, and in fact, like at the end, they're pseudo or quasi like Gaussian distributed, right? So per pixel, we have like a Gaussian distribution here, and which means that now those two look the same, and we can like just sample Gaussians to get those seedings, right? And then again, this is happening in an analytical way, like the addition of the noise, and then the removing of the noise is basically learned then in this case. And again, this is like the discretized way of thinking about this and so on. And this was leveraged also in terms of behavior generation by this amazing work by Cheng Chi under the guidance of Sharon Song, who's by now back then in Columbia. Now she's actually at Stanford. So this is like really great work. And this was presented in 23 at the RSS conference. And simultaneously, we presented our diffusion policy work at RSS 23. And the difference between those two is, again, this would be the discretized or the DDPM-based perspective, and we offered a continuous or a score-based perspective. So what does that mean? In our case, we actually looked into like different representations of diffusion that are not following this hierarchical VAE perspective, but rather a more mathematical, like purely mathematical perspective or like a physics perspective. And the idea there is that you can actually describe this diffusion process as a stochastic differential equation, right? And there's a work by Anderson et al., not et al., Anderson by himself from 82, actually, that explains that for every forward SDE, independent of diffusion, just in general, for every forward SDE, there exists a reverse SDE, meaning that purely through like the beauty of math, we can undo this noising process, right? It can exactly represent it in terms of like a stochastic differential equation. So yeah. So, and the beauty here is also that T in this case, right, is not discrete, it can be continuous, meaning that we're not restricted to like N or T, capital T denoising steps that we always have to follow or whatever, or that we have to jump between, but we actually can train with like a random continuous value for T, right, which provides a lot of benefits. Furthermore, we follow the so-called EDM perspective, or like coming from this amazing paper by Karas, elucidating the design space. And that offers additional parameterizations like skip connections for residuals and so on. That allows us to tune and structure our problem even more. But in a nutshell, what does this now mean? If we now have again our very structured space and we have our SDE that leads us to this Gaussian or to this known distribution, right? We can learn the reverse SDE to undo this. The only crux of this is basically that in order to do so, we need to know this term here, which is the so-called score function, which is the gradient of the log marginal distribution, right? So the marginal distribution, of course, being like any slice of this distribution here, or like of this depiction, and we kind of want to have the gradient of log of that, right? And that, as you might have guessed, is not analytically solvable, like usually, right? So, but at the same time, we have these amazing models now that potentially can learn this, and this is exactly what diffusion models do. Even the DDPM-based approach, even though it's not structured explicitly, it implicitly also learns this core function. The difference for us is that we explicitly learn this, right? So again, here, you can, like what this means that we can generate images, right? Or we cannot create the samples from this unknown distribution, but the known distribution, the Gaussian distribution, we can leverage to create samples there. And then you follow the reverse SDE process, given the learned score function here, to create these denoise samples. And we can do the same thing for behavior learning, right? So we actually have like then behaviors afterwards. Okay. I don't know why we have these 5 times. Okay, good. So now the question is, what does our SDE actually look like? So don't worry, right? So we're not gonna actually. Oh, there's a question. Sorry.
The 2 spike at the beginning and at the end just signify 2 different classes of images, or
just 2 different, like different modes in your distribution, right? Like you have usually like those spaces that we want to learn about, right? Like for instance, dogs, or like dog images, or like images in general, or like even behavior, right? is not only an unknown distribution, but it's a like highly multimodal distribution usually, right? Well, we don't know what the modes are and so on. But the idea is that by this, like structure means modalities and these kind of things, right? So by basically projecting that all the way down here, right, we basically learn a mapping. Well, actually, this is the learning of the mapping to how to go now from this known distribution to this unknown distribution back. But those are different modes simply in your distribution. Yeah. Can be, for instance, different Docker images, but can also be like let's say different like ways of moving your arm or whatever. Right? Does this make sense?
Yes.
Okay. Something that I didn't mention here, but I think we will mention in a second. So what you see here in terms of like the red and black like squiggly lines, those would be the actual SDEs or the trajectory or some samples from the SDE, and the noise injection term. So like basically this part here, sometimes called Brownian motion or reader process, right? Like those basically cause it to be wiggly. If you get rid of it, you're left with the white lines, right? And you can see that the marginal distribution for the squiggly lines and for the white lines is the same. So that's why we usually refer to this white part as the probability flow, ODE, right? Because it becomes an ordinary differential equation because it doesn't have this noise injection terms anymore. Okay. So what does our SDE actually look like? So we selected a forward SDE that already contains a score function, right? Following the score-based diffusion and the EDM-based formulations, right? And the beauty of this is that if we have the formulation like this, again, over here, we only have like F and G, right? F and G, and we can select what F and G is, right? So those are just like placeholder functions. So in our case, all of this would be F, and this place would be this part would be G, right? So by formulating F like this and G like that, it allows us to have a reverse SDE which looks almost identical, right? So the reverse SDE and the math is actually quite trivial or quite easy to derive. So if you have fun, like in terms of deriving equations, go ahead and do this. But the only difference is basically this sign over here. Where's my cursor? I lost my there. This sign over here, right? And this is because we're now basically going in a different direction in terms of production. But that also implies like other things that make basically the learning problem a little bit more like easier and more efficient, right? So yeah, furthermore, some additional information how we actually parameterize this. So we actually say our score function is not only directly the neural network, but it is like a function of the neural network, which contains these skip connections, and that is also following the EDM formulation, which makes the whole thing much more robust and much more efficient in terms of learning, right? So and then finally, something that is interesting is that the way that we train this is over the so-called score matching loss. I don't think that we will not ask for equations of derivations in the exam of diffusion, right?
Equations maybe, but we will not have to know them. Like we will get an equation and then we can ask like, what does this term do or this term, this term.
Yeah, good. But again, so right, so we basically can get rid of the injection and the noise injection that leaves us with the probability flow ADE. But the beauty of this one, of this formulation, actually is that this is the exact same as flow matching. So if you have flow matching with Gaussian noise, which in image generation you don't really have, right? Or you can have, but not exclusively. Whereas in behavior generation, almost every method uses Gaussian noise. Then those two become equivalent, right? Score-based diffusion, the stuff that we're doing since a couple of years now, and flow matching, which is the new kid on the block, are virtually identical if you have Gaussian noise, right? And it's not us claiming this. There's actually work backing this up. Yeah. Okay. So now hopefully you understand this depiction, right? So you understand now that we don't have like the generator and the decoder or like an encoder decoder mirror and like generator discriminator anymore, but we basically are left only with a generator if you want, or only with a decoder, right? Or rather actually a denoiser, right? That's what we do. So now how can we introduce this?
What are reasons for
Speak up, sorry.
What are reasons for not using Gaussian noise?
Oh, you use a different type of noise. You can use like pink noise, uniform noise, like
Why?
maybe because like the Gaussian noise doesn't represent your actual like let's say observed noise distribution in your data, right? Who says that images basically have to like the distribution over the pixels or whatever has to be Gaussian, right? So there's different benefits of different noise formulations, right? But Gaussian is often used simply for the fact that we can do a lot of analytical stuff with Gaussians that we cannot easily with other noise or with other distributions. Yeah. Okay, so now to finish up, how can we introduce disentanglement here now? Well, we actually have a paper that will be presented this week in Alberta, right, on this. And to give you a little bit of a motivation there, why we would want to have like disentanglement, or how disentanglement actually can help you in performing better, because so far we treated it as a kind of a trade-off, right? So we have disentanglement or we have better performance, right? But we actually can show that it can help with performance, right? This disentanglement part. So when will this be, for instance, the case? These days, if you actually look out into what all of the models have, right? So they kind of use like this multi-modalities, right? So be it different perspectives of the same scene, right? So for multiple cameras, or be it, for instance, like tactile information or like lidar information, these kind of information, right? So, but like this quiet assumption that everybody does, that nobody talks about, is that there's this understanding that the information is continuously and noise-free available, right? So we actually assume that the noise is always there, right? Oh, sorry, not the noise, the image is always there, the information is always there. But in practice, if we actually deploy these models, right, in the wild, it might very well happen that some of the sensors become unavailable, right? Let's say like a camera on a self-driving car becomes dirty, right? Or damaged or something like this, right? Or like the cameras or the sensors of our robot also can get affected, right? So you understand that part, right? So there's like, that's very clear. So what can we do now in order to deal with this? Like any ideas, any suggestions? Sure.
There are a few things you could do. You could either train the model with black and white data and, well, you train it to deal with that. And the second thing you could do is give the model some kind of mechanism that's different than typical updates that deal with this.
Not sure what you mean by the second one, but let me rephrase so the answers were like we can either train the model with like some kind of blackout in the sensor data, or we can introduce an additional mechanism that deals with the sensor in a way, sensor information in a way that allows for sensor information to not be available. Is that what you're saying?
Just have separate update mechanisms. One for if you have an actual sensor reading for a specific sensor, and one for not having that.
But that basically would, like, if you say different update mechanisms, you're talking about the training, but this would also imply that during inference, you have different models for different sensor availabilities.
Well, okay, so you have one update step that is for time update and one update step for sensor readings. And if you don't have a sensor reading, then you just do not do the update step for that specific sensor reading.
But what does it help you in your inference? Like if you say update of the parameters, fine, right? And that's kind of like going in a similar direction of the first, like as you suggested in the first plan, but during inference, what happens during inference?
Your model does not try to compute something that isn't there. And it doesn't get confused by the absence of it.
I mean, don't believe that will work that way. But maybe we talk about this in detail. Like, you're welcome to talk about this offline, because there are some issues with this. But yeah, but like, let's go along the first route that you suggested, right? Like this blackout data, something that maybe also actually even address the second suggestion from you. What people usually do is dropout. Have you guys heard of dropout, right? So the idea in dropout is that you basically for like about n steps or like every n steps or like 10% of the time, basically say like, oh, this data point is actually not available, right? And you can do this on layers, but you can also do this on input data, right? And say like, okay, now we don't have this information there. There's like a no information token, for instance, if we use like transformers or something like this. But that doesn't really help. Why does it not help? Let's analyze what the problem actually is in this case, right? So if you train your model normal through backpropagation, these kind of things, right? Then the issue is that in your latent space, right, there is no incentive for the model to make your latent space unnecessarily complex than it has to, right? So which means that if I train this model and there's part of the latent space which is covered by one of the sensor data of sensor information, right? Then this one basically will get the bit to be like, oh, this camera, this encoder is responsible to produce this part of the latent space. Does it make sense? Right? So now if you have information which is available by multiple ones, right, what will happen? Like only one of them will actually end up producing that information, right? Because there's no benefit in having multiple ones leveraging this or like producing the same part of the latent space, right? Because during training, there's like you basically just like backpropagate most likely the gradient along one of those paths, right? So there's no benefit in that. So what happens if we use dropout? We would assume that hopefully now the encoder would also be able to like reproduce separate parts, but in practicality, like if we actually look at the latent space afterwards, so this is the so-called TSNE plot, which we'll talk about later today, still like how to produce those. But if you look at those, each color represents like a different sensor modality. Trained with dropout now, even in this case, the latent space is the disjoint, right? So basically each camera has their own part of the latent space that it covers, that it takes care of, right? So what does that mean? For instance, like this one covers the position of the rim, this one covers the base of the robot, and this one covers, for instance, the position of the backbone or something like this, right? So each of those informations are in our latent space, but they're basically only produced by one of those, right? And that's a problem. Does it make sense? However, as we just discussed, there is this shared information. So for instance, in our case here, we have basically the rim that is present in two images, right? And there's unique information. There's information that only is available to one of those sensors, right? Like for instance, the base of the robot. So instead of hoping that the latent space or like the encoders basically learn to share this information, right? Or like several encoders being able to produce the shared information, we explicitly enforce it, right? So we introduce shared and private encoders, which we'll talk about in a second. But with this, we actually get a latent space that looks like that, which is exactly what we would expect. There's private information, so information that can only be generated by one of those sensor modalities. And there's a cluster of shared information, basically meaning information that can be produced by the same or different, or like by multiple cameras at least. Does it make sense? So with this now, we basically are able to deal better in situations where we have things missing. Of course, we don't do magic, right? If there's private information missing of this camera, it's gone, right? We don't have access to this anymore, but the shared information will still be produced by other spaces. Does it make sense? Okay, so how do we do this? We take our normal encoder stage, but now we have two types of encoders. We have private encoders and we have shared encoders, right? So the private encoders produce whatever we assume, like where we want the private information to be, and the shared encoders produce whatever the shared information should be. So with this, well, we do this by introducing or by using the info NCE loss, the info noise contrastive estimation. And the idea here is again that the info NCE loss is a lower bound, or info NCE in general is a lower bound on mutual information. Again, you see mutual information comes back, right? So we already like talked about how this relates to disentanglement, right? So the idea here though is that we approximate this by having this contrastive idea that we say like, okay, we take data points that have like a high mutual information, or like that we assume that these data points have a high mutual information, and we attract them to our latent representation, right? So basically we want to say like whatever our latent vector reproduces should be close to whatever the positive sample is, right? Given an anchor point. And the ones that don't share or have little mutual information, those get pushed away, right? Those should go somewhere else. Does it make sense? I know we didn't have a 5 and 5, and see what happens if we don't have a 5 and 5 in a while. You guys don't pay attention anymore, right? Like, so this is we're close to the end. Let's push through. So just for you, again, you don't need to know this by heart, but this is what the info NCE loss looks like, right? And you can see here already those little positive examples, the X pluses, and the negative examples, the X minuses, and X without any sign is basically our so-called anchor point, right? So we basically get 1 point, and we say like, okay, the plus has like a lot of mutual information with this anchor point, and it should be encoded like this, and the minus has little information with the anchor point, it should be encoded similar, right? So little mutual information. So what does this look like for us? Since we basically don't want to use any additional labels, and don't want to have like this manual labeling what a positive or what a negative example looks like, right? We do this in a self-supervised way, meaning that we use already information that we have. And one information that we have already is the temporal axis of this of the data points, right? So now, for instance, we take the wrist cam, right, and the shared information, and we say like, okay, if something happens at time step t, and for the wrist cam, and I have this information that is contained in my wrist cam, at the same time step, right, a different camera for the same time step should contain the same information, right? There should be shared information between those two different views for the same time step. But this different camera at a different time step should not contain this information anymore, right? At least that's the assumption that we're taking. So we're basically saying like, okay, like same camera or like different camera at same time step, positive example, different camera at different time step, negative example, right? For the shared information. For the private information, we now say, okay, private information is something that is private to the sensor itself. So it means that for time step t, for the wrist camera, we say there is some private information, right? But the same information, because it's private to the camera, not to the time step, right? The same information should still be available at another time step, right? So we basically say like a time step t dash, we have a positive example, like something that shares a lot of mutual information with our anchor point, right? And a time step, like and any other different perspective, no matter the time step, should not have that same mutual information for the private encoding. Does this make sense? So this is how we basically disentangle now the shared space into shared and private encodings, right? We add an additional orthogonality loss that for the same perspective pushes them apart, right? Just to increase the disentanglement even more, right? Between those. And then, of course, we have our diffusion loss, the score matching loss that we just described, right? And this goes into all these conditionals, into our denoising process, right? And now we basically do follow just the normal, the score-based diffusion here. And the cool thing is what we can see is that, as I promised, we wanted to show how this disentanglement can improve the behavior, right? So if we now look at just the normal behavior, no noise, no disappearing cameras and so on, we actually perform better, significantly better, right? On several benchmarks. So in this case, I show the Colosseum benchmark, right? But the really amazing part is like, and same happens also, by the way, for the Libor data set. But the amazing part is that if we now start removing information, right? So we basically add significant noise on the cameras, or we drop out the camera altogether. So we mask the camera, right? So we black it out. We see that we still maintain very strong performance, right? Compared to not doing it, right? So here, for instance, even with dropout, right? Or like just the baseline method, we're around 20%, and we still maintain, even though one camera is entirely missing, still maintain 60% accuracy or performance, or success rate actually in this case. And again, we can see this trend across different benchmarks, right? So even this is just 20% performance, but consider that you remove 50% of your available information, right? So you remove 2 cameras, and you're still able to perform with 20% success rate, which is quite remarkable. And furthermore, we actually even can show that now, without removing any noise, we become much more robust to perturbations. So meaning different objects and so on, right? Why is that the case? Because this information now somewhat like focuses on the things that are actually relevant, really, right? So this is the disentanglement thing, instead of focusing on everything around it. So we can also see this a little bit in terms of interpretability. So if we actually now use the saliency maps for those different embeddings, so we project our different embeddings back onto our saliency space, right? Like onto image space, we can see that there is, in the private encodings, there's information that appears to be, again, this is like the illusion of interpretability for saliency also, right? that seems to focus only on information that is private to that embedding, right? So to this camera. So for instance, this is the only camera that ever sees the end effector, and that's why it focuses on that. Whereas on the shared one, it appears to be on parts of the scene that are relevant for the task itself, instead of like the camera perspective.
So compared to a method that doesn't do
Again, I can
compared to a method that doesn't do this, even when the test data does not have any missing information, does this improve the performance?
So this would be these evaluations, right? So where you have a masked none, or here also it views none, and yes, it does, right? Because you can see the baseline. So this will be the one without anything. So this will be the baseline for just vanilla behavioral cloning, right? Without our disentanglement, and we have like almost 20% higher success rate here. And even for score-based diffusion approach like this one, we're also at almost 20% higher success rate.
And the architecture is completely different.
Completely the same.
Okay.
Well, it cannot be completely the same, right? Because the architecture doesn't have two different like encoders. So, right, but basically, imagine if you would have no info XE loss and only like either the green or the pink one, right? But that would be, other than that, would be all the same.
Then you would have more calculation and more parameters, right?
In what
In
way?
the DSPC.
Because
you have two encoders per.
Right. Yeah. I mean, what you're arguing is basically that because I have more parameters in total here, right? So there's more representational power that I can have, right?
Yes.
Like, yes. I think we evaluated both, and I don't think it made a difference, but like, I'm not 100% sure. Like, but it's definitely in the paper.
Okay.
Yeah, and the code base is also online available. Yeah. And yeah. So and with this, we're basically at the end of the lecture now. And now you've seen like how we can introduce disentanglement, and even how disentanglement in diffusion actually can be used to improve performance instead of being a trade-off. Because this was one of the, I think, very early questions today. We're still going to do a 5 and 5 before we do before we go into break. Okay, let's do 5 5.